It's interesting. Some of the most interesting research topics, at least that's interesting to me, are converging to be the same problem from different fields. What I'm talking about is, on the one hand, the idea of algorithmic game theory, or in other words, the idea that you have algorithms that pursue certain strategies. And within that context, we have the problem of blockchain design, blockchain voting systems design, long-range attack defense of blockchains, like all those things, which I find incredibly interesting. It's not exactly down my alley. I'm not a cryptographer by training, but I can see the ideas and the interest that really comes through that. And what I'm actually trained in is economics, and I had very good training in my undergrad with Professor Fair at Zurich in experimental game theory. So I would say I'm pretty well versed with game theory. So the idea to use that, or the concept of game theory as applied to other areas than just economics, and this is the key. When we learned this in economics, it was all about, okay, how do people act? How do people actually deal with incentives and all that kind of stuff? And that's great research and should be conducted. But we have this whole new slew of problems now, which is algorithms or digital persona that act in certain ways, and sometimes strategically, sometimes not, and etc. Within a whole other context, so a very different setup is self-supervised reinforcement learning. Now that maybe for the people that are directly involved, it's obvious, but I just think that the connection maybe warrants a little bit of explanation. Why is that? Why is that almost the same problem? Well, it kind of is, because in self-supervised reinforcement learning, you really have to think about the reward functions, the cost functions, when you do self-supervised reinforcement learning, because the only input you have as a human or as a designer is the actual development of the algorithm that moves the object, which is, if it's a Go playing algorithm, then it's a Go playing algorithm. Maybe it's going to be a car in the future or a robot. That object is moving according to certain objective functions and incentives, and that's really what you designing as a designer is reward functions and cost functions. So the purpose of this podcast is to give people a sense of what it feels like to run a hedge fund, and we have covered lots of ground here in terms of talking about Orange Capital Partners as a fund, talking about our strategy, talking about the principal stack, talking about sometimes we just have daily gains and losses, very mundane things, and sometimes we talk about books we're reading. And I think one of the more important things, actually, probably the most important thing at all, is what kind of research are we doing? What are the long-term projects that we think we should be spending our time with? Whatever you do, whatever you're doing on a daily basis, that's who you're going to be in 5 years. So it's almost paramount to think about, okay, what is it we're actually doing? So I want to talk about this in this particular episode. This is the Not Even Wrong podcast. It's September 4th, 2022. This is Krim Delko. For the year, we are down 33.5%. The market is down 18.2%. We're underperforming by 15.3%. Now, again, what are we doing today? What is actually going on a daily basis with the fund? And I think I want to talk about the connection between the one research topic that we're most interested in is the topic of algorithmic game theory, just for lack of a better. I don't think there's a real word for this yet. That's why I'm struggling. I think algorithmic game theory is probably the best sort of encompassing term for all of this. And what it means is, and let me talk about, I want to do this in a preparing way. So I want to read from right to left. So instead of trying to define what we're working on, how about I just find an explanation for what we're working on. So what we're doing is we're researching the thing that is helping us design algorithms to pursue certain strategies with hopefully also having outcomes that are desirable. So here's the thing, like when I when I was in college and all that, and I used to learn about algorithms. The idea was always algorithms are there, let's say, to pursue a certain goal. Like, for example, an algorithm would be how to define sales for Amazon, how to execute sales for Amazon. That's an algorithm. Or how to trade on the New York Stock Exchange. That's an algorithm, and that's already, by the way, an interesting topic, because that's market design, and that's already, I think, crossing the border of just sort of, let's call it, transactional algorithms versus algorithms with open-ended outcomes. And I think that's what we're interested in here at Orange Capital Partners, is algorithms with open-ended outcomes. Why are we interested in that? Because it covers two very interesting fields that we're interested in. One is the blockchain technologies, and the other is self-supervised reinforcement learning / AI. And I think it's actually the same problem, and that's what's so exciting about it. So let's say if we do some work on blockchain design, that's what we've been doing the last few days, was thinking about blockchain design, thinking about long-range attacks and how they can be prevented by let's say proof of stake platforms and their designs, and how they interact with agents and potential adversaries. So all those kinds of questions, they all morph into what's called blockchain design. But then the same problem, just from a different angle, or like just ask a different question. Instead of asking what kind of blockchain should I design, how about I ask what kind of algorithm should I or can I use self-supervised reinforcement learning to build an AI that can drive a car? Same problem, because at the essence the problem is the same. What kind of cost and reward functions do I use to actually execute something like that? So that's what we're interested in right now. So what are we doing? Well, we're one of the things I've done is courtesy to A16Z or Andreessen Horowitz, I've listened to their research seminar they had a few weeks ago about all these things. So from long-range attack strategies, or prevention of long-range attack strategies, towards zero-knowledge proofs and things like that. That's, I would say, general blockchain research, algorithmic design research, and there's some very interesting people there. So we've been listening to those presentations. I also revisited my Berkeley course that I've done, I think, about 2 years ago now, on blockchain technology. That's just a basic course on, what is blockchain technology, what are the sort of okay, one of the problems in blockchain let's dive a little bit deeper. So what are we talking about here? So blockchain technology in general is just a bunch of transactions that get put together on a certain ledger. We call it a blockchain. So let's say a block encompasses a bunch of transactions. They're algorithmically defined, and those transactions are then put in a block, and then the block is chained towards another block, and so on and so forth. And that's the blockchain. And we have the problem is, how do we validate those blocks? How do we make sure that whatever's going on that blockchain is legitimate? So that's what blockchain technology is trying to solve. And the Byzantine fault tolerance issue is, okay, how can we have a decentralized platform that makes sure that everything is okay? And that's solving the Byzantine generals problem, which the Nakamoto consensus has solved, which is proof of work. Proof of work just means you have to invest a lot of resources to make sure that the blockchain is okay. And anybody who invests these kinds of resources has an incentive to keep the blockchain sane and accurate, instead of making it not accurate. And therefore, Nakamoto consensus with proof of work as a fundamental basis of that allows for a blockchain to function. Now, that is very expensive, and people have tried new things, and one of them is proof of stake, which is what Ethereum is trying to do and others are trying to do, which is a little bit different. It answers the question. The question is the following: who validates the blockchain, and who gets access to that validation pool? And the answer in proof of stake is, well, the people who have stake. So meaning the people who have stakes in the actual, let's say, in the coin of the blockchain. In the case of Ethereum, they have ETH, and they stake their ETH to be able to validate stuff, and then they get compensated for that. So that's the kind of research which is being done now. That in itself is, of course, very blockchain centric, and certainly not something that maybe self-supervised reinforcement learners or people like self-driving car people or board game artificial intelligence researchers, they might not think of this as a first sort of order of business, meaning, oh, I should use some of those techniques for myself. But if you really sort of zoom out a little bit and you think about the problem is we have a decentralized system, or an algorithm, if you want, that is functioning under the constraint of the laws of physics, human incentives, fear and greed, and all of those kinds of things. And then we have certain outcomes. And this is where I think once you zoom out that much, you actually get to see that it's very similar. Because again, we have algorithms that are focusing on some sort of design pattern that eventually gets an outcome that is desired. And it's decentralized. It's completely not centrally planned. So this is not AWS run by Jeff Bezos top down. This is not Microsoft Azure. This is a decentralized platform. This is the key problem here. And I think what's so exciting about the decentralized platform, in particular, let's say something like Bitcoin or ETH, is that you can't really choke. There's no throat to choke. This is the fundamental idea of the blockchain technology paradigm, if you want, that allows us to think about possibilities of organizing a society in a very new way. But I'm going a little bit too far, because I don't want to talk about blockchain technology and its purpose right now. I just want to talk about the actual research topics. And again, the research topic, very fundamental, is simply, how am I going to organize a blockchain so it can't be attacked and the validators are doing the job that I want them to do. And see, this is where it's so tangible, because I don't know what kind of people will join this platform. I don't know how the system will evolve into the future, but I have a certain idea of the kinds of outcomes I'm trying to achieve, and how do I design the platform today so the outcomes can be achieved. This is the key. And this, by the way, this is just a tangent. This applies to something like a social network also. And this is why this is so interesting. Once you have certain solutions, you could apply to different domains. And the fundamental problem is, okay, we want to design an algorithm in such a way that outcomes are achieved independent of the environment, but we have certain constraints that we have to put in. And I think the constraints, let's say in this particular blockchain problem, is of course greed, the fear of adversaries, and let's call it human nature. I mean, that's really the constraint here, because we know, let's say we could have a beautiful decentralized network like Ethereum. If we assumed everybody is a good actor, we could have a great social network, and we don't have to worry about it. But we don't. We know that there will be bad actors. There will be be it North Korea, Ukrainian hackers, Russian hackers, whatever it is. There's always somebody who will hack the system, and therefore we have to be one step ahead. And this is the interesting thing. But and before I now let's talk a little bit more technical, because this is really interesting. It's interesting to think about the technical aspects of a long-range attack. So what is a long-range attack? Let's say we have a proof-of-stake system where validators stake their, let's say, ETH in Ethereum, and then they get the right to validate transactions. Now, an adversary could potentially, let's say, steal the private keys of the validators and pretend to be validator X while they're not. So North Korea could pretend to be a validator and steal the private key. So stealing the private key, that's more of a cryptographic problem, in a sense that it's it's like stealing the key of your house and then robbing your house kind of thing. But then you still have to think about it from a network perspective. Okay, how do you deal with that once it happens? And then let's say Ethereum has this thing called slashing, which is if that happens and they just slash all the ETH that is being staked to do the validation, basically they punish the person that has been stealing all that stuff, and then somehow they reimburse the people that have been stolen, probably. I don't know the details, but you see, this is the kind of thing you have to think about very deeply, because you don't want to be in a situation like ETH was a couple of years ago, where they had to, basically go reverse transactions way back and then reimburse people and so on and so forth, because you want to make sure that the blockchain, as it is today, is really that's what it is, meaning that's it, that's the state of nature today. You don't want to always have to think, well, it could be reversed, because you have composability, so you're building on top of the blockchain, you're building contracts, smart contracts on top of the blockchain. So if you don't know, you have to kind of assume that the present is really the reality, the truth, and that there's no way back, and that's kind of one of the problems that I think people like Vitaly Buterin and all his people around Ethereum have, and again, some people are saying ETH is a shitcoin because proof of stake doesn't work. It has to be proof of work. I don't know. This is beyond my understanding. I think I understand the problems, but I just don't have an answer, and I don't think anybody has an answer right now. So we're doing research, and that's the beautiful thing. We're doing research. We're building knowledge. We're conjecturing, we're trying out things, we're experimenting. And this is what's so beautiful about this space, and I think that's why it's so interesting. Now, there's other proposals, let's say in the A16Z videos, this lady, the Russian lady, I forgot her name, who is sort of the crypto person at A16Z, she talks about something called Winkle, where she proposes that validators, that users, so if you use, let's say, Ethereum, you also, by using it, validated by staking your coins and validated while you're using it. So she's kind of trying to combine the incentive of using with validating. So instead of separating it, so the way I understand it is, the analogy would be that instead of having lawyers and then people who transact business, that everybody is a little bit of a lawyer themselves. While they're doing business, they're also making sure that whatever they're doing is legally and legally, in a sense of the protocol, okay. So this is the way I understand it. Again, these are proposals. You can feel the freshness of the subject, because all these people, Tim Rothgren, I think is his name, he former professor at Stanford, now research at A16Z. He actually wrote the book Algorithmic Game Theory, so he's an expert in these things, and you can see even him, he's definitely tapping sort of in this fog of interesting opportunities, but there's not enough substance knowledge there, which is, on the one hand, of course, something we want to change. We want to get more knowledge, but the good thing is there's also all the stuff, the egos, the hierarchies, well, I've been doing this for many years, all that stuff is been thrown out of the window, because nobody can really say I've been doing this for many years, because it's so new and fresh, and it's great. And I think you can see adults with PhDs and all that kind of tapping around like little children, trying to figure out new things, and that's great. That's where new things happen. That's where new businesses, new wealth is created, and new science happens. So having said that, now let's transition to the other problem that we have so much focus on here on Chicago Partners, which is self-supervised reinforcement learning. Now, to be clear, we're not sure yet. Again, in a sense, it's not like a foregone conclusion that this is going to be the future of AI. However, we believe that AlphaGo Zero and Mu Zero, which is what DeepMind has been producing in the last couple of years, are really the path forward when it comes to artificial intelligence at a new level. I don't care if it's human level intelligence or not. All these things are irrelevant to me. But I think I want to just say one thing when it comes to artificial intelligence. And again, shout out to Brad Hall here, because Brad Hall had this really fantastic review of a conversation between Sam Harris and Max Tegmark, professor at MIT. They talk about AI. And what's really interesting about this conversation about AI is it seems like they both don't really understand what AI actually means. That's that, oh, well, we have this intelligent system called AI. We humans are very intelligent, and there's different types of intelligence within humans. And the highest level of intelligence is the type of intelligence that can actually think about AI. So the people who think about AI right now are those who are concerned about AI, so we should take it seriously. Something along those lines. And
Brad Hall is attacking those views and brings in a Popperian view of things.
well, we shouldn't think about AI that way. AI is the ability to solve problems, and we should have an open mind towards what it actually means. And in a sense that if we have a super intelligence that can solve certain problems, then why should that super intelligence become vicious? And I think the fundamental problem that Brad is actually pointing out here, I think, is the dichotomy between, okay, well, we have an AI which can be incredibly powerful. I think the AI itself, if it's that powerful, will almost by definition also follow moral and ethical principles that so-called good people would follow. The problem is, of course, that AI could be used by bad people, and that's a different problem. That's kind of like nuclear power. Nuclear power in itself is a neutral technology. It's just a technology, but of course, put in different hands, it can be very vicious. So I think that's a conversation we need to have, and not necessarily if AI itself is good or bad. I think I completely agree with David Deutsch and Brad Holm that AI in itself, if it follows the actual epistemological fundamentals of knowledge creation and knowledge refutal and all of that stuff, in itself cannot be that. It's not going to be hard. It's a good thing. It's like saying, well, we shouldn't go to school because, well, if we create smart people who create smart things, they could be bad for us. Well, again, it's good. I mean, progress is good. Knowledge creation is good. And if we have digital forms of knowledge creation, which is what we call AI, that's good too. How do we put that in people's hands, in humans' hands? That's a different question. Back to the question of AI. What is AI? Again, in a Popperian view, AI is the ability to solve problems, conjecture, solve problems, create better problems, ask the right questions, and so on and so forth. That is AI, and that in itself is a great thing. Now, the question here, when it comes to practical application, is, okay, which type of AI should we pursue? Should we do the supervised machine learning that we've been doing in the last 10 years since ImageNet competition and the breakthrough that happened in Toronto? Should we do that, or should we, Jeff Hinton and these people, should we pursue that path, or should we do something else? And we at Orange Capital Partners are of the opinion that the path of just more practical usage and better usage of machine intelligence is going to be the mu-zero type path, which is a generalized model of self-supervised reinforcement learning. And that's where the rubber meets the road when it comes to algorithmic game theory, when it comes to blockchain design, algorithm design, because again, we're dealing with something where we have certain constraints, we have open outcomes, but we have a certain idea of where the outcomes want to be. Let's say we want a car to be able to drive itself. We want that. Now, how do we achieve that? We can do it the Tesla way, which is have all these different tasks, or we can try to do the mu-zero way, which is we start with zero and then build through self-play. We have the thing learn itself, and we are of the opinion that the latter is going to be more successful. So that's kind of what I wanted to discuss in this episode. To summarize, we have the problem of how to design algorithms with given constraints and open outcomes. And we have two different fields, practically, which from a zoom out perspective actually merge towards the same type of problem, which is really how do we design algorithms that achieve certain outcomes under certain constraints. Used in blockchain technology, we can prevent long-range attacks and create blockchains that are more robust and cheaper to maintain. Used in AI, we can use, hopefully, the mu-zero approach or self-supervised reinforcement learning in a generalized way to solve robotics problems such as, for example, self-driving cars and robotics in warehouses and so on and so forth. Thank you.